I'll ask a question to myself and then try to answer it. So this is something that I somehow feel very unhappy about, because I feel very unhappy that I didn't have a chance to talk about it yet. So, namely, I want to look at an example of a category of D modules on something that's not exactly, well, not as simple as a scheme or a smooth scheme, even though it is smooth, and try to figure out what the category looks like. And in fact, the answer already appeared at some point, because so when you look at, so if you believe in the classical field theory, which is in fact a theorem, then there's supposed to be an equivalence between the category of D modules on band GM and the category of the derived category of quasi-coherent sheaves on log Cis GM. And I told you what these objects look like, so let me remind you. So band GM has a abelian variety in it. Then there's Z. So this is times. I'm just writing it vertically to match the two columns. And then there's there are also automorphisms. So there's also BGM sitting in it, while on the right-hand side there's something classic, not just classical, just some usual algebraic variety. This is somehow the first way to understand the space of local systems, and this is an extension of the Jacobian by a vector space. So then there's also BGM, and then there is something non-classical, meaning DG. I don't know if there's a well, DG. So this is the spec of, I guess, not a spec of K eta, where the degree of eta is equal to -1. So the shifted version of the ring of dual numbers. The terms on the left-hand side and on the right-hand side match. So D modules here are match with quasi-coherent sheaves here. D modules on Z match with quasi-coherent sheaves on BGM. And D modules on BGM are supposed to match this.
Where does this K eta come from if you don't use this model with the complete intersection there?
But where does it come from on the right side? Well, you can see it from the deformation theory, because there's H2. So you can say that this eta is somehow what is responsible for. I mean, if you try looking at this, you know that classically this is supposed to be smooth. That's a smooth stack. But then you try computing its deformation theory, and the deformation theory does not look like a deformation theory of something smooth. There is this H2, which is supposed to be about abstraction to smoothness. Now, fortunately, it does not really, in classical sense, we would say that it does not really affect smoothness, because we have the same, somehow it's parasitic. It's the same H2 at all points, and it doesn't actually do anything. But it's our indication that, in fact, there are some non-smooth directions, and so that's them. Is this satisfactory? All right, so this is what I wanted to talk about. Now that you know what I have in mind, is this acceptable? Are there any other questions?
Why did we poke out a point when we were computing folks? Is this a uniformization? Is it something that makes?
Well, why do we have? Why is it okay to pick a point, or why is it necessary to pick a point? Okay, so it's not really. You can say on one level, the only reason I'm picking a point is so that I get this decomposition completely explicitly. For instance, even classically, here I'm writing Picard of my curve as a product of Jacobian and Z, and that depends on choosing a point. So this, if I choose a point, that gives me. So the advantage is that I can just write product and don't think about in terms of extensions of groups on both sides. Of course, the price you have to pay is that this is not canonical. So another way, so somehow another reason why I wanted to pick a point on the spectral side. By the way, I don't remember what term was used, so spectral and Galois side refer to the same thing. So because it's supposed to be the spectrum of Hecke operators on the atomorphic side. Anyway, so on the right-hand side, that's unambiguous, there are, you can use this point picking thing to somehow convince yourself that these DG directions, that's another way to see these DG directions explicitly. And that's also a very natural thing to do, because after all, these are supposed to be local systems on a projective curve. What are local systems? So you're supposed to do things like write some matrix elements of connections on a projective curve. How do you do this? Well, you cover it with charts, and then you say, I want a section here, I want a section here, I want to say that the two agree. This is some modification. I'm saying, let's consider section on one open set that is has a puncture, which means a connection with a pole, and then I impose the condition that there is no pole. So this is, on a certain level, this is built into the definition of projective.
And it's okay in the sense that if you take several points, then you're going to get the same answer.
Yes. But of course, if you want a canonical answer, then you'd better use that. There was also a very neat and very clean definition of this. By writing it as a pre-stack, by saying explicitly what it means to have a family of connections. But the answer is not completely trivial, because we have to define families of connections with arbitrary DG parameter spaces, not just classical spaces. By the way, I'm actually wondering how easy it would be to see something like this using something more in the spirit of Atiyah and Bott. So just first, somehow, have you thought about this, Dennis? So can you define log Cs? Suppose you want to define log Cs as a DG space by first saying what it means to have a family of C infinity connections, and then imposing the condition that they are actually flat. No, I'm also sure you get the same answer, but it might be something. Well, maybe in some sense it's more. You get something larger because there are more parameters involved in writing this C infinity connection and more equations. But hopefully you should be able to see this. Right, and by the way, this is all another thing. You can also, well, I guess if you do the Betty version, then you have to make. Yes, so in other words, just representations of the fundamental groupoid. So, yes. Does it make sense? Oh. Any other questions? So, all right, so let's look at this object. And now I have a chance to ask questions, maybe also somehow to wake everybody up. So maybe it's just me who's asleep. So do you know any D modules, any local systems on BGM? What are local systems, say, on BGM? What are they supposed to look like? Okay, there is the trivial one. That's cheap. Okay, anything else? I'm glad you didn't say the zero local system. So at least it's. So any other local systems on BGM? So yeah, I mean, somehow the unsettling news is that this is the only thing. Like if you're thinking in, at least if you're thinking in terms of the abelian category, so if you just look at local system of vector spaces, not complexes of such things, so complexes of vector spaces, I mean, then you really only get the trivial local system, well, I guess, trivial local system of arbitrary rank. So there's only the trivial local system, which, roughly speaking, I mean, normally we would say that a local system on the classifying space of something should be representation of this something. So the fundamental group of this, of B, G, is supposed to be G. Now the problem is that here we're supposed to look at the representations of GM that are locally constant on GM. And because GM is connected, that nothing happens. So the other way to think about it is that, remember, this BGM can be constructed as a quotient of a point by GM. So there's a standard symplectic realization. So I don't know. I mean, unless somebody stops me, I'll get to the definition of natural numbers or something like this. So at some point, it should start to get boring. So let me know when that happens. So I'm just saying that, of course, but I'm going to need this diagram anyways. So of course, I need to give a vector space here. Then I need to give an isomorphism between two lifts of it upstairs. But this isomorphism is supposed to be an isomorphism of D modules or of local systems. So it's supposed to be locally constant. And, well, this is connected, so it just has to be constant. And then it also has to be 1, essentially, so that we get a co-cycle condition. So there's no way, there's no gluing really going on. OK, I'm sorry if this was too trivial. But anyway, so there's only the trivial local system exists. However, there is still something interesting going on. Right? So there are X. So by the way, if we're thinking of D modules as right D modules, I should probably denote this local system by omega BGM. So I'm still supposed to look at X from this omega BGM to itself. And, or maybe I should look at, let me not do something that trivial. Let's look at maps as a DG, as a complex of vector spaces, the DG vector space. And in other words, this is just the cohomology of GM. So, of BGM. So now the cohomology of the classifying space, I mean, this is a standard topological fact. This is not, they are non-trivial. Right? So this space, it's in fact, let me write. So this is a free algebra with one generator in degree 2, which I should probably denote by C for Chorn class, but then this will be completely. So let me just write it as Xi, so K of Xi. So in other words, we have this so this is maybe the simplest example where you have maybe not necessarily the simplest, but at least one of the most natural examples where you have a derived category that's not the derived category of the corresponding abelian category. So if you just look at the abelian category, you don't see this X at all. So, and again, I apologize for saying what some of you or most of you probably know, but I think it's a good idea to review these things from time to time. So, right? Okay, so now what we know is that this category of D modules, there's essentially one local system. So if you have any complex of local systems or D modules, any cohomology in it is supposed to be direct sums of these guys. So in some sense, you would expect that anything can be constructed from this one. So that the category of D modules has to be generated by this one object. Now, this is the endomorphism algebra of this one object. So it's natural to expect in such a situation that the category is actually equivalent to the category of modules over this endomorphism algebra. Right? So no, there's no bun anymore. So is this category of D modules of BGM just the category of K of Xi modules? I really don't know. So all right. So, well, I mean, the answer is no, it doesn't match, obviously, but do you know why? So how can this possibly fail? We expect this because if you have an object, a generating object, and you know its endomorphisms in the derived sense, then you should know the entire category. If you want to construct some object from this one, well, you can construct it as a cone, but you know how to take cones because you know what endomorphisms are, you know what are allowed. Then you can consider maps from something into this and take its cone. But again, this all is supposed to be describable very explicitly. And so somehow the behavior of things in this, when you start taking extensions of this guy, it's supposed to look as exactly like taking extensions of the free module on the right-hand side. So on the right-hand side, the free module it's a perfect module, though they generate the whole thing. So on the left-hand side, we also know that there is essentially nothing else. So everything is an extension of this guy. So somehow naively you would expect such an equivalence, but it fails. So what can possibly fail? Well, but we just checked. There's nothing. Yes, but if you have something in many degrees, you can obtain it as an extension of things sitting in 1 degree, sitting in, right? So you can just take a homology and obtain it by successive extensions. So the trick somehow that is to understand that, well, the word, when I say that an element generates something, this can actually mean one of two things. Either you only allow extensions, cones, or you also allow colimits, or you're allowed to take direct sums. So as long as you only consider things, consider something that might be called local systems. So as long as you only look at complexes that have finitely many cohomology groups, and these cohomology groups, we might even not need to assume that they have finite rank, but let's assume they have finite rank so that they're honestly obtained as extensions of this guy, the picture will match. It will just match with, if it will match with finitely generated complexes on the right-hand side. So there's somehow a category that might be called DG local systems on the left, and it matches with the category of all complexes on the right. But it turns out that direct sums, this equivalence, does not respect direct, well, it's not an equivalence. So this would-be equivalence does not respect direct sums. So by the way, explicitly, what is this equivalence supposed to be? This is supposed to be the functor of taking global sections. Right, so this is just the de Rham cohomology. This maps. This is the so this is sends f to maps from this trivial local system to f, which is just fancy way of saying de Rham cohomology with coefficients in f. And so, yes. Where? Oh, you mean what happens on the right-hand side? No, it's actually smaller. So, right, and so somehow the point is that this functor does not respect direct sums, and somehow the reason for this is the infiniteness of this diagram. So this does not respect direct sums or exclamation point. In other words, the problem is that the object that we are using is it's a generator somehow of the category of local systems, but it's not compact. That's more or less equivalent to saying that this, by definition, equivalent functor respects colimits. So it's not compact. So, and you can see this non-compactness when you try to figure out how to actually compute the de Rham cohomology. That computing the de Rham cohomology, I mean, what does it mean to have a horizontal section of something? Or so naively, you want to say that you need a section here, then you need some data on double intersection, some data on triple intersection, and so on. This is what we usually say. But when we say on so on, that means you need somehow the entire collection together. So what I'm trying to say is that this process involves some kind of limit, or if you like, some product. That we need to have the whole thing given together. Purely formally, I can say that Homs in this category, in category BGM, are computed as limits of Homs on these terms of this cover. And it's a limit. And this is a colimit. So limits and colimits don't like each other. So this is why the functor does not commute. And this is why the functor does not respect direct sums. So, however, now that we identified the problem, it's very easy to fix it. In fact, the easy way of fixing it is to replace. So we now know that we just picked a bad generator. So the most natural generator is a bad one. So let us pick a good generator. That is to say, a compact generator. And the easiest thing to do is just, it turns out that formally it is easy to prove that such a compact generator can be obtained by starting with a generator for sheaves on a point, just one-dimensional vector space, and pushing it forward to be GM. So this is somehow a version of the Rham push forward, which was not really discussed if I believe correctly, was not really discussed here. But now somehow this is a sufficiently simple situation where you just have something that's very close to usual D modules. So hopefully I don't need to say too much. After all, we've been writing the Ramka homology all the time. OK, so this is the push forward of K. Notice that the fibers of this map are just multiplicative group. I don't know if it's many fibers or one fiber. That depends on how you count sticky points. But so the Ramka homology of the multiplicative group sit in 2 degrees, in degree 0 and in degree 1. So this object will actually have it will have 2 cohomology sheaves, 2 cohomology D modules, both of them isomorphic to this. So this is an extension of trivial local system by its shift, but this extension is cooked up in such a way that the result, so the claim is that this is compact, and that's a relatively easy claim once you figure out what's being said here. The compact generator. And the calculation shows that it's now that its endomorphism group, so the maps, or endomorphism algebra, maps from this object to itself. Maybe I should call it something. So let me call it, it's a generator, so I might as well call it G. So maps, G is not a group anymore. So maps from G to itself is just exactly the algebra with one generator in degree -1. And so this is, in fact, we can use now this generator to define the equivalence between the 2 categories. So the category of D modules on band G, on BGM, is equivalent to the category of, to the DG category of modules. What was Xi is in degree 2. So this cohomology, it has 1 generator in degree 2. This is the first Chern class, which is. I'm sure I wrote something about it. Maybe I erased it. OK. So this and so yes. Yes, but I mean, I guess all algebras here are somehow automatically DG commutative, so eta square is 0. And now, in fact, we can now understand why this, even though this equivalence did not work, it somehow almost looked like it did. So this is what was discussed in, this is one of the examples of this whole story. So this is what we discussed yesterday, yesterday morning, is that this category and this category are related by the Kazul transform. So it is the Kazul transform identifies this category with the category with int core of this category. Now the category of modules, this basically the quasi-core category. So it is smaller than this one. So this, in other words, you can, so if you might remember that, so int core, let me, well, that's a good exercise, how to make direct sum fail. Yes, but you can take different shifts of omega. So I think the easiest thing would be to take omega and start shifting it to the negative direction and take direct sum of those.
Can you give examples? So on the left-hand side, you have omega.
Yes. Sorry, can you? Oh, if I start with omega here, what is the result? Is this sheaf of principal parts? This not sheaf, this module of principal parts, right? So at least I'm assuming that so if we use the Cazul transform to go from here to here, so this is one. So one way of saying it is that, so we have this D module of BGM. There's the functor, which is very badly behaved. This functor that sends, not, well, it's well behaved on somehow on finite things. So this functor is just de Rham cohomology, which goes into modules on of K of psi. There is an equivalence given by this, taking this compact generator. So these are maps from G. An equivalence with modules. Sorry?
G, what is this?
It's this extension of this guy by itself. Extension of, extension of omega by its shift. Again, you can say that omega has this non-trivial element of x2 from it to itself. So that means that there is a non-trivial extension of omega and its shift by 1. So take this extension, this turns out to be compact. And so somehow the logic is that there is this equivalence, this is modulus of K of eta.
Excuse me, what it means turns out to be compact? So is there some clever reason why?
Well, there is a clever reason. The clever reason is the junction relations for this map, so that it's compact upstairs, and so, yeah. So, and then, but if we want to compare these two maps, well, we somehow have to make sure that they land in the same thing, so maybe we want to add the Cazul transform here. So this will land us in modules, but remember the Cazul transform is an equivalence from int core of this to all the entire category of modules. If we only apply it to this category, it lands in modules, so with support at 0. And this diagram does not commute. In order to close it up, we need to add this colocalization functor. So these are sections supported at 0. So, and one clever way to state what's going on is that we figured out that for this D modules, for this stack, the Rham cohomology is somehow the wrong object to consider. The right object to consider is the Rham cohomology together with this localization, colocalization procedure, which is this an appropriate introduction to your work with Drinfeld? Okay, passes. So this is somehow a general phenomenon for stacks, that direct images and the Rham cohomologies are not always, so the naive version is not as good as it seems, so it's not as good as we would like to, and so it has to be corrected, and this is an example of such correction. Well, almost. Again, it's the question that if you believe in the adjunction, I'm just saying that if you have a non-trivial D module and you lift it up, it's still non-trivial. So that you can, that the pullback is conservative. But that's the point, that omega is not compact, so it's not supposed to be a cone. It's supposed to be a limit, or a co-limit, sorry. So yeah, I mean, you can get it, but it's like asking how do you get K of psi explicitly from just K. well, you look at K, then you construct K of psi mod psi squared, then you construct K of psi mod psi cubed, and so on. This might look like formal power series. Well, actually, it does not look like formal power series because I'm taking inductive limit anyways. But somehow the point is that no. Anyway, yeah. So I'm constructing this. No, that was a bad thing to do. Right? So K. Sorry, I messed up. See, I messed up the two sides of this. I'm not supposed to be constructing K of psi from K. I'm supposed to be constructing its principal parts from K. And then what I said actually is correct. Any other questions?
Is the category you get bigger or smaller than the...
Well, is the category of sheaves supported at 0 bigger or smaller than the category of sheaves supported anywhere? Is the question. Okay, so no, I mean this is a full this is a colocalization, meaning it's adjoint to a fully faithful embedding. All right. If there are no questions, then.